I've got this going out, I've got this coming in, I want to make sure it's the same thing, so let me naively put the equality between the two. And therefore what I find is that evolution is in fact actually an automorphism of some kind, or a morphism of some kind, similarity transformation of some kind. This is my hypothesis. Let's see how far we can go. No, I'm still doing it wrong. Now I wonder if that equation will come. This is ridiculous, isn't it? Never mind, I think we can see how it works. I think we can see how it works. What I do is then, okay, to make sure I'm not completely out of it, although I may well be, can I reproduce, can I get somehow back to differential equations of motion with changes in time, rather than, and have commutator brackets. This is particularly the sort of thing that Alan Conn actually takes as basic in his non-commutative geometry. You identify these, saying what unfolds, refolds again. And then now I'm putting in something. Let me assume that m can be written as an exponential like that, not saying what h is at the moment, but we know what it's going to be. And this tau is some sort of enfolding parameter, if you think about them. And then just do it for small changes. You get this equation out, but you get that equation out. Of course, if you go to the limit, that gives you essentially if you replace the idempotent by the density operator, and this is what I was talking about breakfast time, and the density operator for a pure state is an idempotent. So that you're looking here at essentially the Liouville equation. So you've got the Liouville equation out of this very simple model. Whether you want to believe it or not is another matter, but from this very simple model you actually get the quantum Liouville equation out. And now, okay?
So
your
thinking here is that m is equal, m1 is equal to m2. It means really this, I mean, in kind of analogically speaking, that you mean to say that the n4 and n-formant
are the same
identical.
in this particular case.
Yeah,
but now I'm trying to get a sort of a way of thinking which could be generalised.
Yeah.
You know, what would happen if they're not the same? Can we have some other kind of movement and so on, which is not just confined to quantum theory? Quantum blobs. I know Morris has accused me of pinching his ideas. Of course it's your idea. Can I now get a more detailed mathematics in a phase space by taking that Liouville equation in the form it's in? That means identifying some idempotent from somewhere. And I go to the Weyl algebra. I've got the Weyl algebra. Okay, is this the Weyl algebra you use as well?
Yeah, sure.
Okay, because there was I was discussing with someone, and someone was saying, "Oh no, Freddie uses a different." I think it was you, Ray. Freddie uses a different.
No, that's the one.
Okay.
I don't know. There's no polynomial.
Yeah, we were having a. Well, perhaps we do it later on.
It's just that relation, yes.
Yeah. Okay. And now what I want to do
Within V and the A's.
within that algebra, I want to form this idempotent, where this is the V from here, this is my vacuum projector, and this is my U from here. Okay? Now it turns out that this is the idempotent that von Neumann used in his 1932 classic paper to show that the Schrödinger representation was irreducible. Because that's a primitive idempotent. And when you've got a primitive idempotent, you know you can't reduce the representation and you move from there. Now, if you now project into, and I'm not sure mathematically what I'm doing when I bring in this. I know what I'm doing physically, because this physics we always do that. Sandwich an operator between a bra and a ket and see what
The
happens.
question, I mean, what's the omega?
There's a vacuum expectation value. This one here. The reason, you can see why I can't use V, because I got V as well for the, I'm running short of symbols.
Yeah.
It's that thing.
what is it in terms of the final algebra? In terms of U and D?
No, it's adding.
Okay.
Remember I said I had to add. Now whether it's actually in the final algebra, we can argue about that, but I came to it by adding it to the Heisenberg algebra, and then knowing that you exponentiate Heisenberg, blah, 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 you get final algebra.
But from now on actually made some sort of a vector. Didn't he?
I'm doing what he did essentially, but in a very different way.
Okay.
He just plucked it out of the air, because Fabio and I spent, I don't know, about 2 years repeatedly looking at this von Neumann's paper, saying, where the hell did he get that from? He got something like this. He just stuck it in, without explaining where he got it from.
But then,
So carrot.
Sorry for that.
Should we have a discussion? No, okay. Sorry, I'm going. Can I go on a bit more?
Yes, please.
Yeah. So and this is the reason why I did this in this one, because this is my quantum blob. Yeah. Oh, in fact, if I do the blob, it's your Gaussian wave. The Gaussian wave back in the phase space. Where I'm getting it from.
It's just a symbol of Laplacian.
Sorry.
It's just a symbol of the Laplacian.
Yeah, no, of course. Yeah, no, I'm sure. But this is.
It's exactly the same as the Gaussian symbol. That's a good one.
Is that interesting?
That's a very
The
good
way I've got it. Have I smuggled something in I shouldn't have smuggled in? But it seems that you don't have to start with all these other junk. You can start here.
Well, A and B are.
They're just parameters. I mean, you have to work it out. Do the integrals, and it's a mess. I can't put it on. Yeah. They're sort of functions of alpha and beta, I think. I can't remember, but the point was to get is the block. It's also got a Fourier coefficient in. Now then, if we now use this only now using the x representation on both sides, then look, it turns out to be the Wigner distribution. So this is what I meant, that you can get the Wigner distribution from the Liouville equation plus the idempotent. And he calls this a characteristic function because he's brought up as a statistician. And they always use characteristic functions in statistics because that's somehow easier for them to use. I mean, Ray's here being.
Could you just in a few sentences say what it means in statistics?
Right?
Or
it's basically it's the Fourier transform of the probability density.
And it's easier to work with that Fourier
And
transform.
I mean, because it has probably when you take sums of independent variables, the characteristic